Hope you are all enjoying your evening so far. No? Yeah? Yes. Thank you for sticking around as we are getting prepared for our next segment of tonight's session. We will be having a performance. Meanwhile, feel free to stretch in your seats, and do not forget to check out after this session is over. And yeah, thank you so much, and do your stretches. Thank you.
As you can imagine, it's very difficult to follow such an inspiring presentation. You have to have an outlier. And fortunately, you're ready for your next outlier experience, one that has the potential to redefine or at least broaden the way you think about music. Eduardo Miranda is an academic colleague who likes to live at interfaces. Tonight, he'll talk about the interface of music with quantum computing and AI, which has been his primary interest for the past 3 years of a career that began with a PhD at the University of Edinburgh in artificial intelligence, moved through Sony's R&D labs in Paris, where his job was to project human emotions onto robots, and back to music, which was his first love, and he's been a professor of music at Plymouth University in the UK for the past 2 decades. In his opening presentation for Winter Enrichment last Sunday, President Byrne made the important point that outliers in science and technology often live at interfaces between disciplines. Interfaces are indeed good places to look for doctoral dissertation topics. There is a well-known fruitful interface between mathematics and music, for instance. The first readily identifiable mathematician in the Western tradition, Pythagoras, started his school in 530 BC. He was also the first readily identifiable musician in the Western tradition. He codified the 12-tone scale in terms of powers of whole number ratios. With commodity digitalization, that mathematical interface expands in all sorts of directions. And what is an outlier in 2025 may shortly become mainstream. In fact, Saudi Arabia is positioned to transition from very little music, when KAUST was founded 16 years ago, to avant-garde music. Professor Miranda and I just visited the Saudi Music Hub in Jeddah, an output of the Commission of Music from the Saudi Ministry of Culture, in a brand new, beautiful building on the Corniche. We found a well-equipped computer music studio there that's open for business among several other studios housed in that same complex. So it's time for KAUST to get with the program of progressive Saudi contributions to world music. If you go to the KAUST library and the search engine online and enter Eduardo Miranda for author and music for subject, you will get 84 hits, including several books that Eduardo has edited for Springer, with the rest being articles in books tracing the interface of music with such diverse domains as particle collisions from the Large Hadron Collider, enzyme interactions, cellular automata, and virtual worlds. He has studied human-computer interactions in the context of music and in mitigating the effects of human dementia with music. His research includes the mathematical foundations of music, evolutionary music, genetic music, audio synthesis, music-induced emotions, musical expression in performers, musical performer gestures, music notation, music tech, and music software. We learned about Professor Miranda from Samia Falamban, then the director of the Office of Culture, Enrichment, and Engagement at KAUST, who heard him perform at Al-Ula last year. When I was encouraged by Samia to fashion a WEP keynote proposal, I was initially a bit skeptical. I thought the interface between quantum computing and music was frankly gimmicky. I then researched Eduardo and discovered that for most of his career, he has been a serious classical composer. I listened to several of his orchestral and choral compositions, which I highly recommend, by the way, and I decided that his grounding in traditional music legitimized accompanying him into his foray into more experimental styles. So now I'm deeply grateful to Samia for the introduction. In the composition that you are about to hear, called Moment States, Eduardo uses a quantum machine learning method based on quantum reservoir computing to listen to a human performer and then produce polyphonic responses during the performance. The hardware-software environment is called Sphinx from Moth Quantum, based in London. Moment States, whose world premiere was 2 months ago in November 2024, includes pre-synthesized, insonified physical phenomena, live keyboard playing, and a computational interaction. Professor Miranda is leaving behind for the KAUST library one of his books called Thinking Music, one of his classical CDs called Mind Pieces, and amusingly, a vinyl album. This is a vinyl album called Cubism with a Q. It's quantum music, but sentimental guy that he is, he issued it on analog vinyl. Following Eduardo's brief keynote, he will move to the piano and synthesizer set up at the other end of the stage and perform Moment States. After that, the co-founder and creative officer of Moth Quantum, Harry Kumar from London, who is no stranger to Saudi Arabia himself, will briefly describe his startup, which has already acquired 3 million British pounds in investor venture capital, and invite your own interest in it. So with that, Eduardo.
Going to go. Yeah, thank you. Hello. First of all, I would like to thank the organizer of this event and for the invitation to be here today. I'm thrilled to be here. I'm very impressed by the whole setup of KAUST, and hopefully this is the only the beginning of collaborations between perhaps my institution and this fantastic university. Thanks, Professor David Kais, for the flattering introduction. My name is Eduardo Miranda. I'm a professor at the University of Plymouth in the UK, where I am director of the Interdisciplinary Center for Computer Music Research. The link for our website is there. And I'm also scientific advisor for Moth, a quantum computing company developing technologies for the arts and music. I visited the museum here yesterday, and I saw this panel that really caught my imagination, especially this one here, which resonates 100% with my work, my ambition, which is to interface between arts and science. And this is where I work, and this is the message that I want to deliver here today, and give you an example of how sciences and the arts can work together and promote the development of humankind. At my university, we are pioneers in combining music, science, and engineering. Here is one of my labs. So you can see a piano with wires connected to computers. So this is the kind of things that we do with my students, postgraduate students, and undergrads. We are a group of about 20 people at the moment. In addition to being a scientist, I would say, I am a composer. I've been working with major symphonic orchestras around the world. So my background is composition of classical, Western classical music. I have been developing AI primarily for music since the 1980s, before artificial intelligence became fashionable. And I'm fascinated by developing AI models to help me to understand why humans make music. how music affects human beings. You know, humans are the only species that make music and appreciate music. And also, I am interested in developing AI systems that help me to be creative, that help composers to be creative, to compose music. So imagine the computer as another musical instrument, as a modern musical instrument that you use as a tool to create. And as a natural progression of my research into AI, I am now investigating this new computing technology that is beginning to emerge, which is quantum computing. And this is the topic of my talk here tonight. Very briefly, this is not a lesson in physics. It's just an introduction to what a quantum computer is. So quantum computers use the principles of quantum mechanics, such as superposition and entanglement, to perform calculations. This allows these sort of computers to solve problems that are currently impossible or impractical for classical computers. As to give you a very brief differentiation, digital computers work with switches, zeros and ones, so that's how they represent information. And there are billions of switches in a computer today to represent information and manipulate information. Quantum computers do this differently. It uses what is called the qubits, the quantum bits, and a qubit can be 0, 1, or a superposition of both. This increases the computational power and the things that you can do with information substantially. But in addition to computational power, for me, quantum computing promotes a different way of thinking. And this is where I think this new technology can open new avenues for creativity, new ways of thinking about making things, making artistic artifacts, composing music, maybe writing poems, and so on. I'd like you to just consider this. Artificial intelligence today is the, everyone talks about AI. But I'd like to make just this observation. AI is just software. And software needs hardware to run. Artificial intelligence today runs on a type of hardware that was invented 70 years ago. It has not changed. It's switches, zeros and ones. Digital machines have not changed since then. What changed is the amount of switches that you can put inside the box. But fundamentally, what the machine is doing has not changed. I believe, because quantum computers are different kinds of hardware, this means that possibly new kinds of artificial intelligence will emerge, because we will be able to develop different kinds of software that will harness what this hardware can do that is differently from what a digital machine can do. And this is what excites me. I think there is probably going to be what's called the fourth industrial revolution with these new machines. When quantum computers are not fully developed yet, but when they are, there will be a revolution in the way we do things. So it's no surprise that many companies are investing seriously in this new, developing quantum computing technologies, and many countries are preparing themselves to embrace this and to exploit the benefits of this new industrial revolution, including Saudi Arabia. The quantum computing industry market size is huge, and it's forecast to increase by 17 billion US dollars with a growth rate of 30% between now and 2028. This is significant. But why music? What's music to do with quantum computers, with this industry? Computers are everywhere in the music industry. You cannot think about music today without a computer behind it. So you have computers as a new instrument in our orchestra. You can see this, that this is happening. This is me in 1912 performing with an orchestra. There are orchestras of laptops nowadays. Kids get together, plug the computers into loudspeakers and make music together. They jam together with laptops. So there are so-called laptop orchestras. Computers are in the studio. There is no music production today without a computer. And in big concerts. So, really, it's not a surprise that if there is new technology coming in, if there is new computing technology, it's obvious that there will be an impact in the music industry. And this is the music industry. It is also huge. You know, most people did not connect the dots yet. So the market size will increase to 70 billion US dollars within the next 5 years or so, and it's growing. The music industry is really big. Not only the music industry per se, but the technology, the industry of the technology behind the music industry, these pieces of software that are in the studio, the instruments that the DJs use to make music for parties and so on. This industry is also very huge. So this is why, combining the music industry with the quantum computing industry, it is very, very big. So, in order to do this, to contribute to this, what we are doing at my university, we are raising the awareness of this technology. We are educating the next generation of musicians, the next generation of DJs, the next generation of people who use computer technology to make music. So we created last year the first ever in the world PhD in quantum computing in the arts and humanities. And we've got a cohort of students already. So these are the future professionals in this field. And I'm very active in promoting this knowledge, the science behind this, the engineering behind this, how musicians can benefit from this. I'm editing books and giving talks. I'm here today evangelizing you probably, trying to raise your interest in this area. So I think it's important that we prepare a quantum-ready community of early adopters. Even if the technology is not ready yet, we prepare people to be ready when the technology emerges. And this is the vision that we have in my university and with other colleagues, like companies like Moth, for example. My colleague Harry will introduce you to it. It's important that education is not limited to science and engineering, in this case, because the end users and the potential beneficiaries also need to be educated. There is no point in developing a technology that nobody's know how to use, how to make the best of it. Now, let me introduce you to how we can use this to make music. Okay? I will introduce to one of the projects that we've developed in my lab, which led to a next system that we developed, which is the one that I'm going to use to perform the music here tonight. So, I am interested in a field that's called generative AI. It's to use AI to generate things. In this case, generate music. I am interested in developing a system that listens to a musician and responds to this musician. So to create systems that are interactive, rather than developing AI that produces music by itself to replace a musician. I'm not interested in that. I'm interested in developing technology that helps creativity, that interacts with musicians, that promotes more different ways of doing things. So the system that I'm going to show now, which is the precursor of the one that I'm using in the performance, is a system that listens to a person playing, and then it builds a program that extracts the rules of how music works. And these rules are then represented in what I call a quantum circuit, which are programs for a quantum computer that is able to then produce music based on these rules. So that, for example, we've got there some musical rules represented in a sort of mathematical way, which are then translated into a quantum program, which is then sent to a computer, and this computer then produces responses to the musician as the concert or a performance is taking place. I'm going to show you an example of this. This is an excerpt from a piece that I composed for London Sinfonietta last year. It's called Cubism. In this little session here, you'll see that the violin plays a tune, and after a few seconds, you will hear some percussive sounds. These percussive sounds are played by the computer as a response to what the musician played. The violin plays now. So the computer is listening. Give some time. So I'm sending this information to New York, to a quantum computer there, that sends data back that's now being transformed into music. So what you saw here was the whole cycle of that slide I showed before. Now, this system which we developed in my university with my group, we then further developed it. And now Moth is turning this into a product, so that in a couple of years' time, this will be available for other people to use. And I will play you a little video here that will explain how this system works.
Sphinx is a generative music application that uses quantum reservoir computing, or QRC. QRC is a machine learning method that leverages current quantum computing technology. Compared to conventional neural network methods, QRC requires much less computational resources for training. In a typical neural network, dozens of layers of artificial neurons need to be trained. This is computationally intensive. Instead, QRC relies on the dynamics of a quantum reservoir layer. A fundamental difference is that only the neurons of the output layer need to be trained with simple linear optimization. Rather than a large neural network, a quantum reservoir operates in the Hilbert space created by a handful of qubits. Sphinx harnesses quantum reservoir computing to generate music. A typical process of music generation with Sphinx is as follows. The system listens to some music. Each note drives the dynamics of the quantum reservoir in a sequence. The measured state is mapped to an output layer to produce the following music note. The output layer can be optimized further to resemble a known music sequence. The new note is fed back to let the quantum states evolve, continuously generating novel music. Sphinx will enable new ways for artists to interact with musical data and generate meaningful compositions with comparatively low computational intensity. With Sphinx, artists can reach new frontiers of creativity.
So this composition I'll play here tonight, it involves Sphinx as the interactive system that I will play, and the system will respond to what I play. So during the concert, everything that is played on this small keyboard here, this one here, this keyboard enables me to send information to the computer system. And then you see I play, and then after a few minutes, or a few seconds even, you get a response back. But I also have other materials that, that are part of my research into making new sounds, making synthesizers, making new instruments. I also produced sounds using data from CERN particle collision system. So basically, in the Large Hadron Collider, they make particles to collide, and these particles then generate a number of subparticles that are distributed in this huge device. And the trajectory of these particles, I take the data and turn them into sound. So these are the kinds of sounds that you hear in the composition. So these are the sonification of particle collisions. Then I also wrote, not AI algorithms, I wrote quantum programs that generate patterns, okay? These patterns are numbers, patterns of data, which we developed in my laboratory with my students. We developed a way to turn this data into musical notes. And so whenever you hear something like this, right? It's a bit chaotic, a bit random, and very rich. So because these patterns are incredibly rich, I was not able, or I would not be able to generate this on my Macintosh, for example. It needs the computational power of a quantum machine to produce this. So I would say that this music that you just heard would not exist if it was not for a quantum computer generating it. And then there is the interactive part, using the Sphinx software that I played the video earlier. So what I did, I input music to the system offline, and I trained the model by sending this data to a quantum machine. because the volume of information that I'm working here is vast, I cannot do this in real time. I had to do it offline. So I sent this to a quantum machine. The quantum machine built the model, and now I've got the model. What happens now, I play music to the model, and the model produces responses based on what it learned. So I trained this machine not with big data. I trained with my music. I played to it. I played my style. I played some things using Arabic scales and so on, so you hear it. And then what the computer is doing is responding to me the way I would have done if I was playing with myself. And this is what I find interesting, this technology, because it does things that are quite similar to what I have done, but there is a difference, which is the voice of the quantum computer. Okay, I think that is that's it for now. Thank you so much. And I'm going to perform the piece now. So bear in mind that this music should be considered as an experiment. Now, as a scientist, go to the lab, make an experiment, see the results, and so on. Because every time I play it, it sounds a little bit different. What I play is always the same, but what the machine makes as a response differs. It may sound nice, may sound bad, so this is part of the experiment. So there will be materials that you may find difficult to listen to because they are too complex for our human ear. But there are other parts that may be amenable. So let's listen to this experiment. And on this screen here, I have is a kind of a control panel where I control how I want the computer to listen and to produce the sounds that I'm playing. So we start with the particle collisions. Thank you. Thank you. So this is what is to come. Perhaps not so dissonant, perhaps not so noisy, but in the last session you could hear that there has some harmonies, some good responses that I would, I would say that they are quite musical. And I think that's where the power of this kind of technology lies. Thank you.
Thank you. Thank you.
Thank you.
And now, to conclude with about a 5-minute description of the hardware tool and the software-hardware package, we have Hari Kumar from Moth Quantum in London.
Thank you. So thank you so much, David, for having us here, and thank you to everyone at KAUST. I'm aware that I'm on a quite tight time, so I will try and breeze through some of this. So I'm Hari Kumar. I am one of the co-founders of Moth. Importantly, I do not have a scientific background. My background is in the creative industries and cultural sectors, but I'm very lucky to be surrounded by people like Eduardo and people like our chief scientist, James Wooten, who bring a lot of that technical expertise. So, who is Moth? We are a quantum computing company developing applications for the creative industries and cultural sectors. And we were founded 3 years ago with a mission to unlock real computational power and potential in the creative industries and cultural sectors. Now, last year, we officially raised our first round of fundraising capital, and things have accelerated since then. We now have 2 offices, one in London and one in Basel, our research lab, where there's actually a quantum computer being built downstairs. So, since I first met Eduardo 3 years ago, we built a number of musical applications on quantum technology. The first was a synthesizer that uses quantum-inspired sound control and is now used by hundreds of musicians around the world. The second was quantum audio, which is an open-source developer library for representing and processing audio as quantum circuits on quantum simulators or on quantum machines. Now, what you heard today was one of the first times Sphinx, our latest generative quantum music application, was used on stage. And you got a glimpse of what is going to be possible in the future. But Sphinx and this quantum reservoir computing backend are not just being used in the context of music. We've actually built a Mario game and generated this level using the same back-end technology, which is quantum reservoir computing. And we're already starting to experiment in the fields of visual media, so image and video, and other kinds of creative applications. And it's not just Sphinx and quantum reservoir computing. Our research team in Basel, in Switzerland, are looking at a whole array of algorithms and approaches for generative technologies where quantum computers, in the long term, can unlock real computational value. So I'm skipping through quite quickly here, but I wanted to introduce you to the team that I lead at Moth. So I'm one of the co-founders, and I'm Chief Creative Officer. I think I'm a bit of an outlier in that sense in the quantum industry. I don't know if there are any other Chief Creative Officers, but of course, we are the only people looking into this domain and developing applications for creativity. Now, within Moth, we have a team called Moth Studios, and our goal is to work with artists and creative practitioners to develop new applications of quantum computing, test our latest research and products, and actually drive what we believe will be a cultural movement around quantum technologies and quantum theory as well. So here are a few of the artists we're working with. Eduardo is, of course, a special case because he works within our team as well as wearing that hat as an artist as well. We have so many artists that we're working with at the moment that I couldn't really, and I don't really have the time to dive into all of the projects. But the reason we do this is what I want to touch on. Since the early computers, and more recently with the latest breakthroughs in AI, artists and creative practitioners are always the drivers of innovation, adoption, public awareness, and many important factors when developing a new technology. Before we had classical computers, the computers that are in our phones but were once, as Eduardo noted, the size of rooms and temperature controlled like quantum computers. Before we had those being used in the traditional industries in the many ways we now know them to be useful today, we had artists experimenting with classical computers, making music, as Eduardo touched on, and making visual images, working with them in artistic practices. And the same was true for the recent breakthroughs in generative AI. I'm sure many of you have used a generative AI application over the last few years, and it's likely that one of those applications you will have used will have been a generative image model or a generative music model. But it's always the artists and those creative applications that come first. And so it's critical to Moth that we engage with these creative practitioners and develop exciting projects. And also a core part of our journey with these artists like Eduardo, is coming to stages around the world like this today and showcasing the latest work we're working on. And I'm excited to say that this year is the International Year of Quantum, backed by UNESCO, and we have many exciting opportunities lined up to showcase all of this quantum creativity from now what is hundreds of artists interacting with this new technology. So, as the theme of this year's plenary is outliers, I wanted to leave you with a quote from one of my favorite media theorists, Marshall McLuhan, who says that artists are the antennae for humanity and possess the power to anticipate future social and technological developments by a generation or more. You may say a similar thing about theoretical physicists, science fiction writers, technologists. Many of you here today who are researchers in your respective fields, working at the cutting edge of those fields and innovating the future. But I think sometimes we forget how critical a role the arts, humanities, creative practices, and cultural production has in shaping the future and predicting the future. And so with a technology as powerful and potent as quantum computing, we are very proud at Moth to be leading this charge of quantum creativity. So thank you very much for listening to Eduardo's talk, for listening to the incredible performance by him, and for entertaining me for a few minutes while I tell you about Moth. Please check us out. We have a lot going on this year, and we're very excited to be in the Kingdom. It's our second time here performing and presenting. And I briefly mentioned two of our early tools that we developed, the quantum synthesizer, Actius, and quantum audio, which is for those of you who are developers and want to build music tools. Please do check them out and have a look. Particularly Actius, the synthesizer, is a no-code application that anyone can use and start getting to grips with quantum computing, quantum theory, and start actually interacting with quantum simulators, interacting with the technology. So, yeah, thank you very much, and it's been a pleasure to be here. Thanks.
Thank you, Hari, and I'd just like to announce that tonight's program was actually co-sponsored by Moth Quantum, and maybe I'll call both presenters out for a final round. I got stretched tonight. I hope you got stretched too and enjoyed what you heard.
Great stuff.
I think we're supposed to have gifts and photographs, but anyway, we'll have the photographs. So this is an early GPS, a spatial positioning system from, the turn of the
Incredible.
Arabic Golden Age.
Yes. Thank you. Yes, sure. Would you like to be in the middle?
Oh, sure.
Yeah.
Thank you.